Okay. So I'm going to say some introductory remarks as to why I think we came together in the kind of unprecedented way we did to form this community that is writing documents, kind of explaining our problems and our solutions. So to get started. Okay. So the big picture for HEP in the 10-year timescale is that ultimately we need to guarantee that we can do the desired physics at the scale and the cost that the funding agencies can actually pay. For a long time we've been limited by offline software and computing costs. Data acquisition systems can drive very high rates, and it's really what we can afford that limits what we collect. So we are driven by the physics objectives of our experiments and the timeline of data taking, the evolution of technologies we use, hardware, operating systems, grids, and clouds, and the resource limitations imposed by our resource providers. So this is Bernd's sort of famous plot of what computing technology can give us over the next 10 years. And what I want you to notice is two things on this plot, that it's a figure of dollars per HSO6. HSO6 isn't my favorite benchmark, but it is something we've measured for a very long time, and so it has some usefulness. And the other thing I want you to notice is the error band here at the bottom. So going 10 years out, depending on whether you're pessimistic or optimistic, you get this factor of 4 between the two. So just for argument's sake, I took a factor of 2. Took the middle between these two limitations. And then on the what the projections say in 10 years to match to that cost for HSO6 has been talked about a lot. At Expo last year, Simone produced this plot, which is CPU for all 4 of the LHC experiments. And you can see from the colors that it's dominated, about 10 years from now, it will be dominated by Atlas and CMS's needs. And then, more detailed on what actually are you spending that CPU on. Well, there's creation of Monte Carlo data sets and creation of reconstructed data. And here's a similar sort of plot out to 2030 for CMS. And so these two groups of estimates agreed to within a factor of 2. You'll have to believe me on that because they use different units. But that's well within this margin that I showed you on the previous plot of this factor of 4. So the first order, we all agree. So putting it together, the projections show that 250 million HSO6 times 2 Swiss francs per gives you $500 million. I'm going to say dollars. I have a hard time with the other. They're almost the same anyway. $500 million just on the CPU, and then you have to throw in the $500 million for storage, and that's comparable with the entire run-for upgrade cost, even including all the manpower. So CPU is the easiest part. Storage is even harder, and in the end, I claimed that this is really unaffordable. And I went through this exercise just because I wanted to put a number on how unaffordable. We've all known it's not unaffordable, right? But to put a number on it, it's huge, right? So we have to do something. And creating the simulation and reconstruction data sets drive CPU costs. And needs for distributed analysis drive the data movement and storage costs. And for these reasons, I will start with the roadmaps of the white paper that outlines the simulation and reconstruction groups work, and then move to the analysis work. And if I have time, I'll go into some of the others. So the simulation, well, simulation is an area in which we have an engine and related community tools already. The GEONT family of tools and its geometry modelers have been around for a very long time, and all the experiments use it, and we've even propagated it outside of our field, space science and medical science, and so it's clearly a big winner and something of high value this field has produced. But mapping that onto where the hardware is going to go in the next 10 years, there is this evolution versus revolution approach to sustaining that. And this working group makes the case that the best strategy for that is one in which GEONT 4 remains the workhorse that the experiments are using in Run 2, Run 3, and that advances in the GEONT V part can be backported to that. And you need that because you need the physics performance validation. You need the experiments to continually be looking at their data and see that the changes to GEONT doesn't make any wild data Monte Carlo variations that show that probably something's wrong. So that interplay is best done with GEONT 4 because it does not require big API changes to what we're doing. And independently, the GEONT V will need to make intrusive data marshalling and API changes in order to get those dramatic speed improvements to take advantage of on solid silicon of the modern chip. So then what you do is you validate the V part against the 4 part, and that's the strategy you would use. You gain confidence in the thing that we will need to use 10 years from now by beating it against the other. And this sort of strategy was, condensed at a workshop that we had in the fall, specifically on this GEONT V family of things. So, of course, there is more that goes into making simulation than GEONT. So the hits that you get from GEONT have to be digitized, and then that digitization really does involve details of the detectors that are specific to specific experiments, or at least to the chips that you're using for the readout digitization. And so that actually can limit the amount of sharing, but it's thought that some of the strategies for doing that and some of the underlying technology, detector technology, is being planned to be shared between experiments, so maybe there are some opportunities there. Some of that's discussed. Then there's this Monte Carlo truth information that has to be handled and passed to the analysis. When CMS first started looking at pileup and keeping Monte Carlo truth information and digitization histories and connections between, a particle and the digi, the size of the event blew up to like 10 gigabytes if you did it for everything, right? So we came out and said, oh, we can't do that. And so we went through a round of trimming down to just the stuff you really need to pass down all the way through the chain, because the analysis is the guy that needs to make that matching between the truth and what came out of the detector. So that's an important part of simulating. And then the digitized signals then are compressed into raw data format of the experiment, and the same reconstruction is run as you would run on the collected detector data. And that's the reconstruction then, in the end, is the thing that really drives the CPU requirements for making simulation samples in 10 years from now, just because the combinatorics of what we do now is so heavy. So there's a simulation plan of work in this community white paper. There is continued work on this VecJam, which helps us map to these more modern systems. We want to promote common solutions for detector geometry, so try to get more people to adopt CD4 HEP. Review that, there's still need for, according to the community, for refining the physics models and the assumptions and limitations that are built into what we have now, especially if those models have to be extracted out up to FCC energies. So improving the technical performance for all of these things, right, that's listed there. Exploring fast simulation options, including frameworks for fast tuning and validation of machine learning. I think you heard a lot about machine learning this morning, so I'm not going to talk about it so much. But it is a promising technique for fast simulating. And even the digitization part, it might be better to model that rather than use our current technique of data overlay. We know we're just going to have to change a lot of our current techniques right now. So those alternatives need to be investigated. So revisit the digitization algorithms, as I said, to improve the performance by means of vectorization. And even though this is hard to share the exact code across the experiments, maybe strategies of how to do this is something that could be shared. So moving on to the reconstruction. The reconstruction group identified broad areas of R&D for algorithms and approaches. They want to enhance the vectorization of the code, algorithms and data structures to efficiently support the core architectures, then algorithms and data structures for non-x86, which we've been relying on for a long time. So how do you use these things? If they will probably become available in the clouds and things like that, and in our HLT funds. And so how much can that give us? That's an area of R&D. So enhanced quality assurance and control approaches for reconstruction techniques was also identified as very important here. Real-time analysis, because this group also with reconstruction for triggers as well as for offline processing. Precision physics, object reconstruction, identification and measurement techniques. With some of the evolution of the detectors, some of this will have to follow. Fast software trigger, I mentioned, that this was also covered by this group, and especially for these high-density environments. And whether it is reconstructing the simulation data or the detector data, reconstruction is the most expensive step, and it will certainly be that next 10 years. So the previous slide outlines the needs and opportunities to achieve affordability for this by working on the software tools and methods. Another avenue of attack is to design detectors with reconstruction costs in mind. And we have some real experience with that in the area of tracking. So the tracker layout, we had a paper presented at HEP that showed what sort of effects just having the geometry of the tracker layout has on the cost of the reconstruction. There's a paper here that I referenced. But one of the things I learned at lunch the other day was Atlas has a factor of 2 difference in the cost of their reconstruction between their LOI layout and their TDR layout. So it is another example of another experiment finding the same thing, that if you can think about reconstruction costs when you design a detector, you'll be ahead. I mean, when you're talking about $1 billion, every factor two helps. So, analysis software facilities. Analysis is one of the areas that is really impossible to separate the thoughts about the software and the facility. Looking back at slide 4, you can see that there is a significant cost devoted to analysis, that big purple blob on the top. And it's an area that's dominated by our least savvy software computing colleagues, usually young students and people that have not been steeped in this field for a long time. And so they make mistakes, and there's lots of room for improvement. So we learned at the analysis ecosystem workshop that while the different experiments draw the line different between central analysis and distributed analysis, we all do essentially the same things. And I think that this is partially the nature of the problem, the need to reduce the data sets. And this is partially the result of using the same data set in the group. So this white paper outlines many promising avenues of investigation established, and it actually even tried to prioritize them at some level. Number one was establishing pi routes. You might wonder, why is that so important? Well, because the rest of the analysis world outside of high energy physics uses Python for analysis. And so we can use a lot of their tools if we make sure that our major tool actually, makes Python a first-class language for analysis. It can become more sustainable if it's modularized more. So there's a call for that. This inventory the needs for bridges and connectors and converters. That is all work that would need to be done if you wanted to take advantage of industry tools. And so investigation of that is recommended. Of course, the interfacing to the machine learning tools, the need to develop work plans. So root I/O performance is another area that the whole field benefits if we put effort into that. Notebook strategies and R&D on new hardware technologies that could affect the analysis tool chain, Spark clusters and the like. And that, the invention of Spark clusters and similar is what ties the facility to the software so much. Okay, so now I'm going to, in a small amount of time remaining, go through some of the other ones that maybe don't have, depending on which experiment you are, don't have so much to do with the cost, but are still very important. And generators is kind of on the edge on that one because, there were talks in this conference about the computing costs of generators, and you can spend as much as you want on them, depending on what leading order, up to the high orders that you need for your analysis, right? So, what we learned by having a group of people get together and talk about this is that different experiments have different opinions about the cost benefits of some of these solutions. So some people spend a lot of money on generation, and some people don't. But it's an area where we do share the same common software because it comes from the theory community. But there's a disconnect sort of between the theory community who, makes these calculations mostly for their own, and they don't and they weren't originally in their scope to make billions and billions of events this way. So, they didn't pay so much attention to the technical performance of their code, and that's creating a disconnect. But, there is an outline of for a white paper on generators, and given the participants I've seen, I have high hopes for this one. that we really will. They really will be able to teach us, a better way forward for generators. Event processing frameworks. So a group consisting of everyone who has ever written an event processing framework got together, and the first step was to define common terms so that we could all be speaking the same language. And then when we did that, we realized, yes, there is a lot of commonality between all the different experiments frameworks. And the real hurdle then is the legacy. Can you actually move to a different framework in the middle of an experiment? Now, I have a lot of experience with that, and I say yes, but then there are people in the group that say no, you can't do that. So one of the things that was said in this one is, well, let's investigate the possibilities of increasing the sharing of the existing frameworks and framework components, and even if possible, to share the whole thing. So that was just left as a question for this. And it's recognized that frameworks have a central role in supporting the porting of applications to advanced architectures, so we had a successful example where the community got together and said, hey, we all need to be using the same underlying thread libraries, and we looked at performances and demonstrators and all settled on TBD, and that actually has been gaining us dividends, because when we went to the KNLs, the TBD library took care to scale us up to the 248 nodes that we can use now because of this library. But there might be other things out there that can, help us use other parts of the silicon that we're not using right now. If somebody decides to put GPUs right onto the chips and things like that. Okay, so enough of that. Then another area is to understand the interplay between workload management and the framework, because there will be trade-offs between a multi-threaded application and a heavyweight cooperative process framework. And maybe in the future we're going to need a combination of both. Right now, an experiment is either one way or the other. Okay, so come up with accommodating multi-level tools like the GeoNB in the framework. That's going to require some work. Okay, so then there's cross-cutting topics. And I put machine learning in cross-cutting topics because it can be used in all three of the areas that I outlined as being the cost drivers. There's a paper on career staffing and training, also very important. The software development and deployment, validation, verification working group. So this is an area that's essential in building on our legacy. And what I mean by that is that the software captures our domain knowledge from everything from the matrix element calculations that encode our knowledge of the universe to the detector understanding is built into the code that we have. And so if we want to make sure that we're not heading off into a wrong direction, we need to do regression testing against what we have. And these systems help us do that. So they're important. And so I had this slide on solved problems. We have white papers on these two, but I'm not going to go into them because they don't drive the cost so much. And so now I conclude. So there is a field-wide large challenge ahead of us on the time scale this year. And limitations of power and cooling and funding will not allow us to keep our current software paradigm or our current mode of computing resource provisioning. So we need to attack this challenge from many angles by maximizing the scientific computing infrastructures available to science 10 years from now. In other words, buy sufficient computing for this, but we know we can't buy everything. By developing innovative and efficient software solutions for the domain of today that we have a good handle on. And designing detectors that give us handles to minimize computational costs throughout the data flow from the detector, the trigger, to all the way down to the analysis insight. So this is a big challenge, but think of the scientific harvest that if we did build up this amount of facilities and capabilities that this could bring us, right? I think it's exciting. So in the face of and then my final word here is that in the face of so much uncertainty, we don't know. There's a whole big program of R&D here, just briefly outlined, and we don't know how much of it it'll pay out and how much of it won't. But we do know how much we need from it, right? So there's a lot of uncertainty here, and it's vital that we continue to talk to each other. And we think that maybe something is, we think we're going down that particular road, and then we learn something that says, oh, that changes everything, and then go off in a different direction without telling everybody else the same thing, that hey, this isn't going to work, So the HSF is planning on continuing having a series of workshops. And it looks like that we are thinking the week of March 26th in 2018. That's the next one.
Thank you very much.
Yeah, thank you for the very nice overview. I want to ask you one slightly provocative question. I think you've been slightly provocative as well in this point. So you mentioned a few times designing detectors with the reconstruction in mind, which is, I think, an interesting idea. But at the same time, we want to limit ourselves in hardware, which once we fix it can't change for 10 years, or
Right.
But reconstruction will certainly get better over the next 10 years.
Yes.
So is that something we really want to take on the same level as, say, hardware designs, which could physically improve resolutions and efficiencies and things?
Well, I think the hardware design actually gives you more bang for the buck in a way than the software. I definitely agree with that. But I think that you can make what you'll see in that paper is you can make small modifications to the layout that make huge differences. I mean, this factor of 2 from Atlas is really something, Another example is timing detectors that allow you to do 4-dimensional reconstruction. So there's an example of a detector concept that really helps the reconstruction, gives it more handles, right, to reject pileup and things like that. So it's this thinking. I'm just advocating thinking about the end result, which is physics, right? And you want to, since we're in a period where we're designing detectors right now, you want to think about both at the same time.
Yeah, a little bit on the same topic, but don't you think that this is already done to the extent that the detectors are designed to be efficient in the triggers, both in the hardware and the software triggers? Right.
Right. So in other words, if you can find tracks in microseconds, you can find them in offline. It's kind of true, but I can just speak for CMS that there is kind of a fight between the tracker community and the trigger community, and it's not clear to me, at least, where that's going to land. Ah, there's the guy who wrote the paper in the back. What do you want to say?
No, okay. So my comment is a bit different. It's not on what I wrote, but more about what can be done in Trigger. Don't forget that what Trigger finds from the threshold of 2G, it takes no effort to do it for it. And displaced tracks and all of that. That's so references to what Trigger do quickly, and that's really.
One of the things you're advocating is using PyRoot to drive collaboration with tools from outside physics. Wouldn't it be more sensible to detach the root I/O framework from root so that you could that way access the root data from other tools?
Yeah, that was definitely discussed, and that's why there's this modularization of root as one of the goals. I think it was maybe second or third or something like that. So indeed, we are advocating that the root I/O be modularized off. And there's lots of talk in the paper about data bridges and ferries and things like this. Creating transparent easy ways of reformatting your data from root into something that a outside tool can easily ingest and use that tool just by itself by reformatting the data. So providing tools to do exactly that is also on the roadmap.
Okay, so thank you very much.